Okay, so for page 14, let me just get this thing out. For page 14, state two uses of capacitors in electrical circuits other than for smoothing a direct current. This is actually the smoothing of rectified AC. Okay, this part here, smoothing of direct current, is actually talking about smoothing of rectified AC. Alright, so there are two other uses for your capacitors. You can actually say that it's used to store energy, or you can say that it's used to block direct current. Why do we say that it can block direct current? Is because your current actually stops flowing when your capacitor is fully charged. Okay, when your capacitor is fully charged, no charges will be pushed to the plate, no charges will be pushed off the plate. So no current actually flows. It's actually blocking direct current. Okay, and you can also say that it's storing energy, but do not ever say it's storing charge. The capacitor as a whole does not store charge. Okay, for B, you have combined capacitances between terminals A and B of the arrangement shown in this figure. The two capacitors each have capacitance C, and the remaining capacitors each have a capacitance of 3 microfarad. The potential difference PD between terminals A and B is 12 volts, meaning to say from here to here is 12 volts. Determine the capacitance C here. So one of the things they did tell you is that your combined capacitance is 4 microfarads. Okay, so what you want to do here is you try to simplify your circuit again. So in my case, you see this one is the circuit drawn exactly as what the question did. This one is C and C. And then this one is 3 microfarad and this one is 3 microfarad. What I could do now in order to find C is, again, I try to simplify this circuit. If I try to simplify this circuit, the parallel capacitances, this is what I expect to see. Okay, so this part here, the capacitances in parallel, I added like I would resistances in series. So this is 3 plus 3, giving me 6 microfarad. So now I would have C, C, and 6 microfarads here. Then when I want to find my total capacitance, this one, because they're all connected in series, I added like I would resistors in parallel. So this one will be 1 over C plus 1 over C plus 1 over 6 power negative 1. So right now, you already know that your combined capacitance is 4 microfarads. So this one will become 4 equals to 2 over C plus 1 over 6 power negative 1. Eventually, C will become 24 microfarads. Okay, so this is actually your working here. Right, so this is pretty straightforward to find your capacitance. This one here for your capacitance in parallel is actually shown here. For parallel combination, C parallel is 3 plus 3, 6 microfarad. Then for the whole circuit, it becomes this. This working will only kind of make sense if you have this diagram here. Okay. Right, then after that, next thing they will ask you to do is this one. Okay, with this, let me just move on. Next thing they'll ask you is to find out the magnitude of your total positive charge. Find out the magnitude of your total positive charge transferred to the arrangement. So for your case here, for those capacitors that are connected in that way, what is the total charge that has been transferred, that has been stored by the arrangement? Even though they talk to you about positive charge here, it doesn't really mean anything. It doesn't really change your analysis. They are really still just talking to you about the charge, magnitude of the charge. Whether it's positive or negative doesn't really matter. Okay, so the one magnitude of the charge transferred to the arrangement, meaning to say the one the charge seemingly stored by your capacitors the charge stored by one plate of your capacitor. So this one, let me just simplify this again. This one can again be simplified further, where I say that is actually equivalent to something like this. Okay, this is what I can say. I can simplify it to a final capacitor whose capacitance is 24 microfarad. Whose capacitance is 4 microfarad. This is what I have. Okay, so this one is 4 microfarad here. Okay, so when you want the magnitude of the charge transferred to the whole arrangement, the magnitude of the charge that has been stored by the whole arrangement, you would generally tend to look at it in this circuit. You simplify all the way to the max. Whatever charge that is stored here will be the charge that is stored by your capacitors as a whole. Okay, because what you can see from here is something like this. If say you had a charge of Q that is being pushed through, your capacitor here will store a charge of Q. And then after that, you work backwards. Whatever Q that is stored here is also the Q here, here, and here. These will all store Q because they are connected in series. And then after that, if you work backward again, for the first two capacitor, you will actually store Q. But then after that, for the last two capacitors here, because you have a junction here, your charge will obviously start to split up. The charge stored will be split. And another thing that you can notice here is because they are equal capacitances, your charge will be split equally. So this one here, let me just try and write it out for you. This one here, you will see equal capacitances. This one is equal capacitances. Therefore, charge is split equally. So here, your charge stored will actually be Q over 2. This one will be Q over 2. This one will be Q over 2. Okay, this is what you can actually say. But now you just want to find Q first. So you apply C equals to QV, Q over V for this one. You know the capacitance, you also know the PD. Your PD is 12 volts because they told you between terminals A and B is 12 volts, right? So this one you already know is 12 volts. You already know the capacitance. You can use C equals to QV to find out what is your Q. So if C is equals to QV, Q is CV, Q would be your capacitance, 4 times 10 power minus 6 times be your PD of 12, giving you 4.8 times 10 power minus 5 coulomb. You want to change it to microcoulomb, you divide it by 10 power minus 6. Divide by 10 power minus 6, you get your microcoulomb. This one will be 48 microcoulombs. Okay, so this one is for this particular part of your question. And then after that, use your answer in 2 to state the magnitude of the charge on one plate of your capacitor or capacitance C, as well as your capacitor or capacitance 3 microfarad. So here again, they now say magnitude of the charge on one plate. So again, it doesn't really change your analysis. Your charge seemingly stored by a capacitor is the charge on one plate of your capacitor. All right. So here, they want the capacitor, the charge stored on capacitor or capacitance C, meaning to say they want the charge stored for this one. So the charge stored for capacitor C, the charge stored for capacitor or capacitance C is Q, is the same Q as this one. So you already found out this Q here, it was 48 microcoulomb. This one will also store 48 microcoulombs. Okay, so that's for this particular question. And after that, they ask you to find out the charge stored on one plate of capacitor or capacitance 3 microfarad. They're actually now referring to this one. So as I mentioned to you, when you try to work backwards, you eventually notice that your charge stored for the parallel arrangement is that they tend to be split apart equally due to them having equal capacitances. So this one, your charge will actually be half. If your original charge Q was 48 microcoulombs, once you reach here, it must be half. If you halve it, it should be 24 microcoulombs. So the charge stored on one plate of capacitor 3 microfarad should be 24 microcoulombs. Okay, so this one is for this. So this one is okay. Then let me move on to another one. Okay, so then next one is page 21. This one. Okay, define capacitance. All right, so capacitance is asking for the general definition of capacitance. The correct answer is charge per unit potential difference or charge per unit potential. The wrong answer is the one that I actually wrote in pencil here. This is actually wrong. Ratio of charge to potential difference is wrong. Okay, now in your class, I never really did explain why is it wrong. This one actually is something related to what you guys have learned in AS before. If you guys remember in AS, there were a few physical quantities that you've learned. Let's just say density is mass over volume. You would have said as mass per unit volume. And then if you have say resistance, it is ratio of PD to current. And then you have say acceleration, or maybe let me just say velocity. If you have velocity, you guys would have defined it as rate of change of displacement. So for these three quantities that are listed here that you learn in AS, you will have noticed that is something divided by something. But in terms of your word definition, they are actually worded differently. Like say for example, density is mass per unit volume is actually something per unit something. And then for resistance is ratio of PD to current is ratio of something to something. And then for velocity is rate of change of displacement is rate of change of something. So those word definitions are specific to those quantities itself. Let's just say when you're talking about density is strictly speaking mass per unit volume. You don't say as ratio of mass to volume. You don't say as rate of change of mass. It just doesn't apply. Okay, so in the case for capacitance, C is Q over V. You'll notice it's also something divided by something. So which one of these is the one that it should be following? It actually should be following this one, the first one, charge per unit PD or charge per unit potential. I cannot say it's ratio of charge to potential. This is what I did over here. This is actually the wrong way of writing it. It's supposed to be charge per unit something. Okay, that's why I say this one, the first statement that I wrote here is wrong. Okay, but say in the event that you are not sure in the exam because somehow you've forgotten what was the correct way of wording it, there is actually an easy way to get the correct answer. That one is by literally rewriting the equations here in Word. Say density is mass divided by volume. If you just say it's mass slash volume, this one will be okay. And then for this one, if you just say it's PD slash current, the slash here is meaning to say you divide. This one is also okay. And then for this one, the velocity one, you just say it's change in velocity slash time taken. This one would also have been correct. And then likewise for your capacitance, if you say you did not remember it as charge stored per unit PD, you can actually just write it as charge slash potential difference. This will also be accepted. So in the last case, in the worst case scenario, you cannot remember any of them, just translate the equation into words literally, then you get the correct answer. So there's one thing to mention here. Okay, now if you look at 2, use the expression for the electric potential due to a point charge to show that an isolated metal sphere of diameter 25 centimeter has a capacitance of 1.4 times 10 power minus 11 farads. So this one here, say this one is your sphere. You want to show that your sphere has a capacitance of this much. So this sphere has a radius of r. You have a potential of V at the surface, which is 1 over 4 pi epsilon naught Q over R, and you have a charge of Q here. Find out its capacitance. You can actually just say that your capacitance for a sphere is 4 pi epsilon naught R. In the last lesson, you've learned that it's not only just charge parallel plates that store charge, but a charged sphere can also store charge. So the capacitance for a sphere is 4 pi epsilon naught R. It actually came from you substituting V into C equals to Q over B. The derivation here is not really required because this is not a derivation question, but as I mentioned in the last lesson, derivation is required as part of your syllabus requirements. So here you do not need to derive it. They just want you to know that C is equals to 4 pi epsilon naught R. Then you substitute in the values. Epsilon naught is the value that you can get from your datasheet under page 2 of your exam paper. And then after that, your R here is actually 25 divided by 2 because what you're given is the value of diameter. So you have to divide by 2 to get the radius. So divide by 2, change it from centimeter to meter. Eventually, you get the answer is 1.39 times 10 power minus 11 farad. So round it up to 2 SF, you get 1.4 times 10 power minus 11 farad, as shown here. Okay, so this one is okay, no issues here. Then after that, let me just go on to part B. Now for part B, you have 3 capacitors or capacitances, 2 microfarad, 3 microfarad, and 4 microfarad that is connected and shown in this figure to a battery EMF 9 volts. Find out the capacitance of the 3 capacitors. So this one should be pretty straightforward. This one again, it often helps to draw out the diagram because subsequent questions no doubt will ask you something about it, which often involves you trying to simplify it step by step. So this one is your capacitor, 3 microfarad, 4 microfarad, and then 2 microfarad. So you would try to simplify the parallel connection first. Capacitance for the parallel one is you adding resistances in series. Is 4 plus 2, giving you 6 microfarad. So this one will become something that looks like this now. So this one would be 3 microfarad, and then this one will be 6 microfarad. So again, you want to simplify this. These are now connected in series. You add it like you would, resistances in parallel. So this one will become 1 over CT equals to 1 over 3 plus 1 over 6. Your C parallel is 4 plus 2 equals to 6 microfarad from before. So your CT is 2 microfarad. Your total capacitance is 2 microfarads. Okay, so this one is pretty straightforward. Okay, then after that, you are now asked to find out the PD across capacitor or capacitances 3 microfarad. So the one that you're looking at here is the 3 microfarad capacitor, which is this one. They want the PD now. Okay, they want the PD across this 3 microfarad capacitor. So again, as usual, do not ever try to use potential divider equation to find the PD, because some people, when they do it to this part, straight away when they ask you about the PD for the 3 microfarad, they think of it as 3 over 3 plus 6 times with 9. The 9 volts here is your P in. So this one is wrong. Okay, you cannot do it this way. So do not ever use potential divider equation here. So one way in which you can now do this is probably by, again, simplifying your circuit all the way to the max. So this one here, you can see that it can be simplified further so that it becomes something like this, where you only have a single capacitor whose capacitance is 2 microfarads. Okay, this one you have a capacitance of 2 microfarad. Okay, so now you imagine now you have a charge that is being pushed through the circuit. The charge that is stored in your capacitor here is actually really just Q alone. It's the charge stored on each plate actually. So this Q, if I work backwards a little, will also be the Q stored in the 3 microfarad capacitor. Okay, the same amount of charge Q is pushed through the circuit. This 3 microfarad capacitor will store a charge of Q. This 6 microfarad capacitor will also store a charge of Q. Okay, so I want to find out the Q that is stored first so that I can find out my voltage. So why do I do that? If you just look at your working here, if I look at the last diagram here, I know that my voltage supply is 9 volts. The PD across the 2 microfarad here must also be 9 volts. From there, I can find out my charge stored. So here, C equals to QB, Q is CB, such that is 2 times 10 power minus 6 times 9, you get 1.8 times 10 power minus 5 coulomb. This is again for the whole circuit simplified. And this charge stored is the same charge stored in the 3 microfarad capacitor. Okay, so when you're talking about the charge stored in the 3 microfarad capacitor, I now know is 1.8 times 10 power minus 5. I now know its capacitance. I also now know its charge. I can now find out its voltage. If I use equation C equals to Q over V. C is known, Q is known, V I can find out. So now, specifically for the 3 microfarad capacitor, if I apply C equals to Q over V, V is Q over C, the charge stored is 1.8 times 10 power minus 5, divide by my capacitance, I'm going to get the answer as 6 volts as my PD. Okay, so now in your working here, you'll notice that you are really only just using C equals to Q over V each time, just that you're applying it differently to a different circuit. The first C equals to Q over V that you applied was actually for the whole circuit. Then the second Q over V that you applied was actually just for a specific capacitor. Okay, so this one thing just to note now. Okay, you are still using the same equation, just that you seem to be applying it for different forms of the same circuit. Then if you look at the last part here, find out the positive charge stored on the capacitor or capacitance 2 microfarad. So again, it doesn't matter whether it's positive charge, it doesn't matter whether it's negative charge, it doesn't matter whether it's the charge stored. They are really just talking about the magnitude of the charge. Because you see, if you think about how your capacitor works, this one, if I still give you a charge of positive Q, it will get deposited on this plate, causing this plate to acquire a charge of positive Q. But again, the same positive Q charge will be repelled off the other plate, causing this plate to become negative Q. So for the capacitor itself, you will always have positive and negative charge on each plate. But the magnitude would always be the same. And when you're talking about the charge seemingly stored by a capacitor, is also still Q itself, because it's always following the charge on one plate. Okay, so here it doesn't really matter how they word the question: positive charge, negative charge, one plate, or the charge stored in the capacitor itself. It's always just referring to Q. Okay, so now they want the charge stored on the capacitor of 2 microfarad. That one is actually now referring to this one. Okay, the 2 microfarad capacitor is actually referring to this one here. It's actually the first diagram here. So how do I go and find out your charge stored here? If you're trying to look at how the charges are flowing or being pushed through your circuit here, you could say that there's a charge of Q that is being pushed, such that 3 microfarad stores a charge of Q. But then once it reaches this part here, you will notice that there's a junction. Okay, so it's kind of similar to one of the questions that we did earlier, but now you cannot just simply say it's Q over 2, because you see the capacitances are not equal. This is 4 microfarad, this is 2 microfarad. So what you will actually end up with is that this one will probably have Q1 being stored on the 4 microfarad. This one will probably have a charge of Q2 that's being stored on the 2 microfarad. Then after that, eventually they will combine back to give you Q. Okay, the junction there, your charge was definitely split up, but now they cannot split up equally because you do not have equal capacitances. So this one, maybe I should just write it somewhere here. At the junction, the charges do not split up equally. The charges do not split up equally because on unequal capacitances. Do not split up equally because the capacitances are not equal. Okay, so because they're not equal, they won't split up equally. So now how am I going to find the charge here? Now this one, you would have to first find out what is your PD across the 2 microfarad capacitor. Because you already know your capacitance, if only you know your voltage, you can find out what is your charge. So how are you going to find out your PD across your 2 microfarad capacitor? This one, you can actually make use of the second diagram here. Let me just try to put those things in again. Let me just erase all the things that are not necessary. If you refer back to the previous working, you found out that the PD across the 3 microfarad was 6 volts. So this one you already know is 6 volts. This one must therefore be 3 volts because you see this one, your voltage supply is 9 volts. If you apply Kirchhoff's second law, sum of EMF equals to sum of PD, your PDs must add up to become equal to your EMF. So if here you already know it's 6 volts, this one must be 3 volts. So this one here, you already know is going to be 3 volts. If you go and go one step further, because here you already know is going to be 3 volts. Yeah, this one here is a bit messy. Because here this one is 6 volts, this one is 3 volts. This one here was supposed to be your parallel connection. If you go and split it back out to your parallel connection, it's going to be 3 volts each. Here will be 3 volts. Here will also be 3 volts. Okay, so you've now found out the PD across your 2 microfarad capacitor. It's going to be 3 volts. So now since you know the capacitance and the voltage, you can now work out the charge again from equation C equals to Q over V. C is Q over V. Q is CV. So take the capacitance, multiply with your voltage. You will get your answer is 6 times 10 power minus 6 coulomb, giving you 6 microcoulomb as your final answer. Okay, So this is one other part to your question. So again, you notice that all the calculations you've done so far really is just using C equals to Q over V. It's just that you're applying it for different parts in the same circuit or different forms of the same circuit. Only then will you be able to understand the logic here. Okay, so let me just clear this thing up. Now, if you have a look at page 73, we already done the first part A, the part where we were trying to explain how is it possible that the two parallel metal plates can act as a capacitor. So this one we say that if you were to connect these two parallel metal plates to a voltage supply, charge will actually be pushed towards one plate, causing this plate to become negatively charged, and then the same amount of charge will be pushed off the other plate, causing this plate to become positively charged. So there's now separation of charge. It is now a capacitor. So here, that's why the answer was worded as you apply a potential difference between the plate, it causes charge separation. Okay. Or the other answer here was also that they say that you apply a potential difference between the plate, it causes energy to be stored between the plates. Because the idea here is that if you push your charge of negative Q to this side, and you push a charge of negative Q off the other side, it involves work, so the work done must have been stored as energy. Okay, so that was for that particular part. Then after that, you have B. Okay, now for B, the arrangement in figure 6.1 has capacitance C. The arrangement is connected into the circuit of figure 6.2. When a two-way switch is moved to position A, the capacitor is charged so that the potential difference across it is B. When the switch is moved to position B, the capacitor fully discharges through your sensitive ammeter. The switch moves repeatedly between A and B so that the capacitor charges and then discharges with a frequency of F. So right now, what you can probably say is that at position A, you're really looking at this loop, because switch A would be, position switch A would be here like this. But when you position switch B, what you're really looking is this. So if I try to redraw it out for you, this one is your voltage supply, this one is your capacitor, this one is your capacitor trying to charge out. This is charging. And then if you are at position B, you are no longer connected to your voltage supply. Instead, you are connected to your resistor. So this one is actually charging. Okay. So when you move between A and B, you are continuously charging and discharging. Okay, so from here, show that the average current I in your ammeter is given by I equals to CVF. Your ammeter is actually this one here. Okay, so what's the average current in your ammeter right now? In your current case, you probably could do it like this. Current is Q over T, all right? Then after that, charge, because current is defined as rate of flow of charge. And then when you try to relate it to a capacitor, capacitor is Q over V such that Q is CV. So you sum it inside here, you will eventually get CV over T. Okay. And then after that, if you try to speed it up even further, you will get 1 over T times CV. Now you can think of frequency as being equals to 1 over T here. So if you equate 1 over T as F, eventually you get I is equals to FCV. I is therefore CVF. Okay. That is one way in which you can do this question. Then if you move on to part 2, for potential difference V of 180 volts and a frequency F of switching of 50 Hz, the average current I in the emitter is 2.5 microamps. Calculate the capacitance in picofarad of the parallel plates. So this one, you can actually just use back the equation that you have from above. Your current is 2.5 microamps, sorry. So it's 2.5 times 10 power minus 6. Your PD is 180, your frequency is 50. Find out your capacitance. Your capacitance is 2.78 times 10 power minus 10 farad. You want to change to pico. You want to have a prefix unit there. You divide by 10 power minus 4 for pico. So you're going to get 278 picofarads. Okay. And for part C, right now, you have a second capacitor that is connected into the circuit of figure 6.2. The two capacitors are connected in parallel. State and explain the change, if any, on the average current in your emitter. So now they mentioned to you that you have a second capacitor. Now, because they just mentioned a second capacitor, we cannot just simply assume that the capacitor are of equal capacitance. So this one thing to note is that this is not necessarily another capacitor with equal capacitance, with same capacitance. They just say it's a second capacitor here. We cannot just simply assume it's another capacitor with same capacitance. So this is not necessarily another capacitor with same capacitance. Okay, we cannot assume it's going to be the same capacitance because they never say anything about that. So right now, they connect a second capacitor in parallel with the original existing circuit. So what they're doing now is something like this. You connect another second capacitor here, like this. Connect another capacitor here, like this. So if this one is C1 and this is C2, because this is connected in parallel, you add it like you would resistances in series. So this one will be C1 plus C2. So capacitance is considered to have increased here. Okay. So from equation I is equals to CVF, your PD applied and your frequency should remain constant because there's nothing in the question that says that it has been changed. So V and F is constant, thus I is directly proportional to C. When your total capacitance increases, your average current must therefore increase. The easy way to look at it would be to think of it as this in equation form. I is equals to CVF, V and F constant would mean that I is proportional to C. So that when C increase, I definitely must increase. So whatever you have in the answer there is just trying to word it. It's just putting it into words, okay? Okay, so have a look at page 37. This one is June 18 P41. It's again talking about your capacitor switching between two switches such that you are charging and discharging rapidly. So for 37, explain what is meant by the capacitance of a parallel plate capacitor. This one just use the definition from the notes. Is charge stored on the plate of the capacitor per unit PD applied across the plates of the capacitor. Just like that. No issues here. And then after that, if you look at B, you have a parallel plate capacitor C that is connected into the circuit as shown in figure 7.1. When the switch is At position X, the battery EMF 120 volts and negligible internal resistance connected to capacitor C. When the switch S is at position Y, the capacitor C is discharged through the sensitive emitter. Right now, the switch is vibrating so that it is first in X, then moves to Y, and then back to X 50 times each second. The current recorded in the emitter is 4.5 microamps. So from here, determine the charge in Coulomb passing through the emitter in 1 second. Okay, so in your case here, when your switch is at position X, we know it looks like this right now. This is actually akin to this. Your capacitor is actually charging up because it's connected to a voltage supply. And then when your switch is at position Y, is talking about this circuit here. This is where you do not have any voltage supply connected, instead it's connected to an emitter. This is where your capacitor is discharging. So they told you that when your switches were switching about 50 times a second, your current recorded is 4.5 microamps here. What is the charge in Coulomb passing through the emitter in 1 second? This one again, you can make use of the equation for current, where you say that I is Q over T. Your current is 4.5 microamp. So it's 4.5 times 10 power minus 6 amps. Your time considered is 1 second. So your charge that passes through the emitter is 1 second. Is really just 4.5 times 10 power minus 6 now. Okay. Actually, it can be deduced straight away now because this one here, 4.5 microamps, is charged per unit time. This one will actually already tell straight away is 4.5 microcoulombs per second. Okay, because it's rate of flow of charge. It's really in terms of charge per second, actually. You can deduce that. But if you want to calculate out, this is the proper way to do it now. Okay, so that one is okay. Now, next one. Find out the charge on one plate of the capacitor each time it is charged. Again, them saying that the charge stored on one plate of the capacitor, this one is really just the charge seemingly stored. Okay. So how much charge is stored on one plate each time your capacitor is charged? Okay, you think about it this way. In 1 second, this one, let me just try and write it in a different manner for you. In 1 second, total charge is 4.5 times 10 power minus 6 coulomb. And then the capacitor charges 50 times per second. Okay, because the frequency was 50 hertz. So this is fact number 1. Fact number 2, capacitor charges 50 times per second. So from here, therefore, for each time capacitor charges, the Q must therefore be your total charge over number of chargings in 1 second. You want to find the charge stored for each time the capacitor charges, you just take the total charge in 1 second divided by the number of charging in 1 second. So it's actually just going to be 4.5 times 10 power minus 6 divided by 50, giving you 9.0 times 10 power minus 8 coulomb. That is what your answer here is trying to tell you. The one I wrote here is actually really talking about the same thing, just that it's thought about differently. Total charge in 1 second is number of times capacitor becomes fully charged multiplied with charge stored on capacitor. It's actually the same thing. It's just that it's written differently here. Okay. Okay, so here, if you're okay with that, next one is find out the capacitance of the capacitor C itself. You already find out the charge stored on one plate of the capacitor. You also know the PD, because if you recall, the diagram actually looked like this. This one was switched at position X. This one was your capacitor. This one was 120 volts. And then this one, you already know that your charge stored on one plate was 9 times 10 power minus 8 coulomb. So when your capacitor becomes fully charged, the one thing we know is that it must always be equal to my voltage supply. So I know the charge, I know the voltage, I can hence find out your capacitance. So take 9 times 10 power minus 8 divided by 120, you get 7.5 times 10 power minus 10 farads. This is your capacitance. Okay. So if there's anything I wanted to write here, this Q here is always the charge stored on one plate, or the charge seemingly stored by capacitor. Okay, but the proper one is actually this now. Q is charge stored by one plate, which also turns out to be the charge that people always seemingly think is stored by your capacitor. Okay, so if this is okay, then you move on to C. Now for C, you have a second capacitor having a capacitance equal to that capacitor C that's now placed in series with capacitor C. Sorry, yeah. A second capacitor with having a capacitor equal to that capacitor C is now placed in series with C. Suggest and explain the effect on the current recorded inside your ammeter. Okay, so right now, this one was your original circuit when it was charging. Right now, you are adding another capacitor to it. This time is in series. Just now the one that we did was in parallel. And also your capacitor here is having an equal capacitance to the original one. So if this one was C, this one is C and C also. Okay. So because this one is connected in series, you have to add it like you would resistances in parallel. So this total capacitance is 1 over C plus 1 over C. Power negative 1 is going to be C over 2. It's actually 0.5 C. Okay, so what do you expect would happen to the current recorded in the ammeter? Because eventually this one, you will have to discharge it. When you discharge it, it's these two capacitors together trying to discharge through your ammeter here. Okay, so what do you suppose would be the current recorded on your ammeter here? So what you could say here is that your total capacitance is half, so your total charge loss will be half. Therefore, your current is also going to be half. Because you can see this, C is equals to Q over V. Your PD would still be constant here because you see this one was originally 120 volts. For this capacitor to become fully charged, it will be 120 volts. For the new arrangement to be fully charged, it also must be 120 volts. So V here is constant, C is proportional to Q. So if C is decreased by 2 times, Q must decrease by 2 times too. So this is number 1. And then number 2 is the fact that current is rate of flow of charge. If T is constant, I is proportional to Q. If your Q decreases by 2 times, current will also decrease by 2 times. That's why you can say current is half here. Okay, so this is the proper explanation. Capacitance half, total charge stored half, therefore current is half. In my case here, I can be a bit more specific in describing the change. I know everything is half, because I know that this is another capacitor of equal capacitance. It's not like the one that we just did. They just say you add another capacitor, but they never once mentioned that it is same capacitance, so we cannot just simply make that assumption. Okay, so there's the need to read the question carefully there.